to the last Andlinger Highlights seminar of the academic year. This is a real treat. This is our inaugural Sigma-Aldrich Lecture, sponsored by Sigma-Aldrich. So I'd like to take this opportunity to acknowledge the Sigma-Aldrich delegation who's here. If you will please stand. Thank you for supporting this lecture. And we're looking forward to continued partnerships with Sigma-Aldrich. Before Barry Rand introduce our seminar speaker today, I think Jim Buntain from Sigma-Aldrich would like to say a few words.
My pleasure. Thank you, Professor Bredas. So it's an honor to be able to be here to sponsor this distinguished talk today. And I just wanted to give 2 minutes background on this. Sigma-Aldrich, as probably all of your laboratories know, you have our chemicals, our materials in your facility. This is very nice, and we thank you for your business on that level. But one of the things we had already spoken about today is the opportunity for some professors, some research groups, if they have materials that are ready to be distributed to other research groups in the world, literally. This is also something of interest for us, and perhaps for some of you, is that we can act to do this. We do this frequently with many professors. Sigma-Aldrich was recently acquired by Merck, a company of Germany, not to be confused with Merck & Co. of the United States, very different companies, although there's a common root 100 years ago. I won't go into that. One of the things that's interesting is I am not from the acquisition of Sigma-Aldrich, but I'm from the Merck KGaA of Germany, and we have a performance materials group. And in the performance materials group, it allows us to have a visit like this, and we can explore other areas of collaboration, other areas of work with interesting places like Princeton University. Even today, organic electronics we spoke of. We spoke of photodetectors both in the UV and in the IR, block copolymer self-assembly, perovskites. I think I'm missing one somewhere in there, but that's fine. So it gives not only the Sigma-Aldrich side of this, but also Merck as a larger specialty chemicals company gives us the opportunity to chat with you. So without further ado, I'd like to hand off to Professor Barry Rand to make the introduction. Thank you for attending and being part of this event.
Thank you, Jim. First, just a piece of logistics. I'd like to ask you all to please silence your cell phones to avoid any interruptions during the proceedings and the seminar that we're about to hear. The seminar speaker we have today, and indeed, as was mentioned, the first Sigma-Aldrich lecturer in the Andlinger Center Highlight Seminar Series will be Jean-Luc Bredas, who comes to us from Georgia Tech, where he is the, let me make sure I get this right, the Regents Professor of Chemistry and Biochemistry and the Vassar, Woolley, and Georgia Research Alliance Chair in Molecular Design. His research is broadly about computational approaches to chemistry as it pertains to organic electronics and many other domains, in fact. And today he will talk to us about organic electronics and energy. Jolie?
But first of all, I'd certainly like to thank Lynn and the Andlinger Center, as well as Jim, Gia, and their colleagues at Sigma-Aldrich for giving me the opportunity to discuss with you this afternoon some aspects of the research we're doing in organic electronics and how it relates to energy. Of course, energy and environment is very much something that's at the heart of what you are doing here in this center, and so I don't need to make you sensitive about the issues there, but I'll take a few general words about energy as a springboard to discuss with you first, in general terms, the field of organic electronics and how it evolved over the past 40 years and the discovery of highly conducting polymers. I'll then go into organic photovoltaics and be a bit more technical, describe to you some of our recent work, especially on the characterization of charge transfer states, and I'll end with hopefully an optimistic note about the future. So in terms of energy, quite a bit of my own thinking has been shaped actually by editorials and books coming from Thomas Friedman, whom I'm sure you know, the editorialist of the New York Times, who has very elegantly, in many editorials, and especially in Hot, Flat, and Crowded, where he refers actually to our planet, has put forward how much energy plays a critical role in many of the major issues that our planet or society faces, going from food and water all the way to poverty elimination and education. And there is a very important comment that he made in Hot, Flat, and Crowded some 9 years ago now, where he indicated that the ability to develop clean power and energy-efficient technologies is going to become the defining measure of a country's standing, environmental health, energy security, and national security over the next 50 years. And if you allow me a short digression here, for 2 years between 2014 and 2016, I was director of the Solar Center at KAUST, at the King Abdullah University of Science and Technology. And in that occupation, I had the opportunity to meet a few times the chairman of the board of trustees, who was no else than Mr. Al-Nemi, who has been Minister of Oil for a few decades in the kingdom. Certainly one of the most powerful men in the world when he was in that position. And it's really striking to me how much the Saudis are looking forward to invest in renewable energy and protect the environment, and how much, unfortunately, in our country, we are not looking at the next 50 years, but it seems that we are going back 50 years. In terms of global energy needs, one way you can quote them is in terawatts. So that means, of course, 1 trillion watts. And to give you an idea, that means the energy or the power required for everyone on the planet, from a baby to a 100-year-old person, running 2 75-watt conventional lamps. And it is interesting to see, and that's the case for quite a few years, then when you look at the energy outlook from the Energy Information Administration, that in terms of global needs, there is pretty much a linear evolution until the horizon 2040. So in 2008, the global needs were on the order of 17 terawatts. They will be on the order, take a couple of terawatts, of 27 terawatts by 2040. The interesting aspect is the fact that in 2008 was still a time when there was almost equal needs among OECD countries with respect to non-OECD. And you can see that the evolution over the years comes essentially from non-OECD countries. And that's perfectly understandable if you think in terms of that very well-known illustration of our planet at night, which actually underlines the fact that 1/4 of the world population does not have access to the electric grid, and providing power to that population is essentially something that needs to happen in the emerging countries. And of course, as you all know, of course, in terms of greenhouse gases, we are now getting levels of CO2 in our atmosphere that has jumped to over 400 ppm in some parts of our planet, whereas it was pretty much very stable between 180 and 280 ppm for the million of years before the Industrial Revolution. So really what we need is a clear need to develop, and that's of course the reason for the Andlinger Center, more energy efficient devices, as well as new devices generating and storing clean energy. And that brings me really to what organic electronics can play in that context. And as I said, we are celebrating this year the 40th anniversary of what arguably is the main discovery that launched the field, that is the discovery of highly electrically conducting polymers. But before I get to that, we're dealing with conducting polymers, but the concept itself of polymer was not always a well-accepted concept. Hermann Staudinger in the 1920s received a letter from a very well-known scientist at the time telling him to leave alone the concept of large molecules because there can be no such thing as a macromolecule. And of course, we all know what has happened since then, and in 1953, Hermann Staudinger was awarded the Nobel Prize in Chemistry for his discoveries in the field of macromolecular chemistry. But that brings me to the point that actually the conventional scientific wisdom up until the 1960s was very much that there could not be anything like a conducting organic material or a polymer. And the 70s brought a complete change of landscape and brought the early days of what at the time was dubbed as a synthetic metal. A first important discovery was made independently in the lab of Dwayne Cohen at Johns Hopkins and in the labs of Alan Heeger and the late Tony Garrido at Penn, who discovered electrically conducting organic molecular crystals with conductivities at room temperature on the order of 1,000 Siemens per centimeter. That's basically the same kind of electrical conductivity as the one you get in the polycrystalline copper wires that we use. The main point that led to that high electrical conductivity was the fact that it's a crystal with an electron donor, tetratiafulvalene, TTF, an electron acceptor, tetracyanoquinodimethane, TCNQ, and while generally in those donor acceptor molecular crystals, you have alternating stacks of donors and acceptors, in this case, you got segregated stacks of TTF and TCNQ molecules separated from one another that allowed the fact that the holes would move along the TTF stacks and electrons along the TCNQ stacks, leading to that very high electrical conductivity. And then there was another discovery the same year at Temple University by Morton Labes and his colleagues. And they took a very old compound, polysulfur nitride, dubbed SNX, which was known since the early 1900s, initially thought to be an insulator. Then with perfecting the synthesis, people realized, well, actually that's a semiconductor. And then eventually Morton Labes was able to get single crystals of the material and discovered that actually it is a metal with also a room temperature conductivity on the order of 1,000 Siemens per centimeter. So SNX is actually a pi-conjugated polymer, of course not an organic system, along which, the chains of which you have sulfur and nitrogens alternating with bonds between sulfurs and nitrogens of the same length. And that's what leads to the fact that it is a metal. It's interesting also, that's a bit on the side, but SNX is still the only polymer that has been reported to become a superconductor, albeit the transition temperature is pretty cold. And also there is another aspect, which is the fact that physicists, as they put it, incorporated halogens into the polysulfur nitride lattice. That means they actually oxidized SNX with, for instance, bromine, and that led to an increase by 1 order of magnitude of the conductivity in the system. In the meantime, that is after the discovery of the metallic character of SNX, Alan Heeger at Penn decided to meet his colleague in the chemistry department. Alan Heeger, of course, was in physics. His colleague, Alan McDermott, and they set up a meeting that started with Alan Heeger telling how amazing it was that SNX is a metal. And Alan McDermott was thinking, well, I know that that tin is a metal. What's all the fuss? And it took them half an hour to realize that actually the SN was not tin, but was sulfur nitride. And so for those of you who remember Alan McDermott, you remember how energetic a person and enthusiastic a person he was. Very quickly, he jumped into that field and was able to make thin films of SNX that actually are looking golden-like. And a little bit later, he was touring Japan, and he gave a talk at the Tokyo Institute of Technology, showed this golden-looking film of the SNX polymer. And at the reception after his talk, because Hideki Shirakawa didn't go to his talk, actually, but he was told that there was that guy from Penn with a golden-looking film of a polymer. Hideki Shirakawa came and met Alan McDermott and showed him his own aluminum or silvery-looking films of trans-polyacetylene. So that's really a pi-conjugated organic polymer. Alan McDermott immediately said, well, you have to come to Penn. And the following year, in the fall of '76, Hideki Shirakawa arrived at Penn. And around Thanksgiving that year, they had the idea, following the idea that was the oxidation of SNX, they had the idea also of trying to oxidize polyacetylene, and that's how they discovered that in that context, polyacetylene can be made very highly conducting through oxidation or even reduction. And so that's really the start of the modern era of organic electronics, even though, as I said at the time, these were called synthetic metals, with conductivities at the time reaching a few hundreds of Siemens per centimeter. And this discovery on these silvery-looking or aluminum-looking films of trans-polyacetylene, of course, triggered a lot of interest in the field, because that was the first time that people saw the potential of combining in a single material, on the one hand, the electrical properties of metals, on the other hand, the mechanical properties that are typical of plastics. So much effort was put into, on the one hand, first, optimizing the synthesis of trans-polyacetylene, especially with Jim Feast at Durham and Herbert Nachman at BASF, and with electrical conductivities in the best highly ordered polyacetylene thin films reaching 10 to the 5th Siemens per centimeter, nearly the electrical conductivity of single crystalline copper. And then there was the discovery that polyprophenylene also can be made highly conducting upon reduction or oxidation, polyprophenylene sulfide, polythiophene, polypyrrole. But the issue was that up until the mid-80s, that promise of having the combination of mechanical properties of plastics with the high electrical conductivity was not fulfilled. Upon doping, those materials were becoming brittle, untractable. And so one had to wait until the mid-80s and the development of soluble conjugated polymers by attaching alkyl side chains, for instance, to the side of the polymer, in that case, initially with alkyl polythiophenes, that one really got into the possibility of using conjugated polymers, of processing conjugated polymers in the same way as other polymers. There is also another extremely important facet that started in the mid-80s with the work of Richard Friend at Cambridge, Ching Tang at the time at Kodak, and Steve Forrest at the time here, in terms of no longer looking at a high electrical conductivity upon, between quotes, doping of the conjugated polymers, but using those conjugated polymers or oligomers in their pristine semiconducting state. And that led to the development of the first organic field effect transistors, organic light-emitting diodes, and organic solar cells. And so maybe some of these gentlemen or some of them will follow in the footsteps of Heeger, McDermott, and Shirakawa, who were awarded the 2000 Nobel Prize in Chemistry for their discovery and development of conductive polymers. So the state of the art, things have changed, of course, tremendously since 30 years ago, essentially because there's been a huge advance in terms of the available molecular and polymer structures, performance and efficiency, and also, very importantly, in terms of device application, in terms of lifetime and stability. And so, for instance, now, if you think in terms, and I'm sure, if not all of you, many of you are aware of the fact that if you look at organic light-emitting diodes, that is, devices that allow you to take electricity and transform it into light, there are no so-called small molecule-based OLEDs that have internal quantum efficiencies that reach 100%. So that means for each electron that you inject into your device, one photon is emitted. The main issue being actually getting all of those photons out of the device towards the person who looks at the device. And so these have brought very efficient devices to the market. And of course, typical examples are the displays of smartphones, of even the Apple Watch. And I couldn't resist to show you that very cool customer. That's a smartphone display panel from AU Optronics in Taiwan. And then, at a larger scale, the second wave of displays are actually the OLED televisions. In that case, that's led by LG. This is actually a picture I took at the window of a department store in Dubai. And the advertisement is that you have a perfect black, and therefore a very high contrast and a very high picture quality. The fact that you have a perfect black with respect to the liquid crystal displays that we mostly use otherwise is because each pixel now emits light or doesn't emit at all. You don't have the need for backlighting like in LCDs that reduces the contrast. And what is interesting, of course, also from a customer point of view is the fact that when those televisions started a few years back, they were in the range of $8,000 to $10,000, and now last week on Amazon, a 55-inch curved smart OLED TV from LG was selling at $13.50. This is a slide that Antoine will remember. I like this slide for 3 major reasons. Of course, if you take red, green, and blue pixels, you put them together, you get white light. And in the mid-2000s, Antoine led a DOE project that involved my group at Georgia Tech as well as the GE Global Research Center. And this is a panel of white light coming out of a polymer. And it is also meant to illustrate the fact that the quality of the white light is really high because all the nuances of the colors of those candles is very well, all those nuances are very well rendered. And then the last point with respect to that slide is that it reminds us that maybe a century ago you would lit a room like this one with organic materials, with wax, and now you're going back to organic materials. And of course, the fact that you have totally flexible devices, you can curve them, you can provide any shape, leads to a dream for interior designers of those luminaires. Audi is very much into looking at OLED lighting, not only for lighting the inside of the car, but also, for instance, for the brakes, where as a function of the pressure that the driver, when the driver pushes on the brake, the backlights then becomes redder as the driver pushes more strongly, so that it informs the person, I mean the driver behind, of whether it's a slow deceleration or if it's something much more worrisome. And then Philips is using also its brand LumiBlade for OLED luminaires, and for instance, by modifying the proportions of blue, for instance, into the white, you can follow, I mean, these are luminaires that across the day, even if you're stuck inside a completely isolated room, can provide for the natural evolution of the light coming from the sun. Okay, with that very broad introduction, I'd like to get a little bit more into organic photovoltaics, realizing, of course, that what one wants to do is to harness the power of the sun that gives us many thousand times more energy or power coming to the surface of our planet than what our needs are. Of course, at this point in time, the market is 90% silicon and 10% inorganic thin films. However, and this is the well-known best research cell efficiency chart coming from NREL, that NREL updates very regularly. The organic solar cells are those solid red dots here. And so the evolution is pretty interesting, but still the efficiency at this point in time remains insufficient for a number of large-scale applications. And these yellow and red dots are the evolution with perovskites, which has been a tremendous, a field that has seen a tremendous increase in efficiency over the past few years. But if you look at perovskites, as well as silicon or other types of inorganic cells, the photophysics is really different from the one that you have in organic solar cells. Indeed, in silicon or perovskites, what happens is that you have a very high dielectric constant, so that as let's say at least in the case of the 3D perovskites, so that as a photon is absorbed in silicon or those 3D perovskites, the hole and the electron can very freely move apart from one another, so you have an immediate creation of free carriers. This is Absolutely not the case for the pi-conjugated organic materials that we are using for organic solar cells. In that case, there are three major components that you need to take into account, not only the lower dielectric constant, but also the very strong electron-electron interactions and electron vibrations or electron-phonon interactions that all conspire to bind the electron and the hole as the pi-conjugated material absorbs a photon. And so you form a bound electron-hole pair, that is, you form an exciton. Of course, if you have a bound electron-hole pair, there is no net charge that's created, and that's the reason why, in the case of organic solar cells, you have the need for two components, one that will be an electron donor component, up to now very often a pi-conjugated polymer, and an electron acceptor component, up to now very often a fullerene derivative. And at the interface between those two components, that's where you get the possibility of exciton dissociation. Right now, in the case of polymer fullerene solar cells, Henry Yan and coworkers, for instance, but there are also other folks like Yongfang Li at the Chinese Academy of Sciences, have efficiencies that are on the order of 12%. In the case of those here, this polymer fullerene solar cell of Henry Yan. You need to have a large interfacial area between your electron donor and your electron acceptor, because that's where exciton dissociation can occur. And so in many instances, and this is the architecture that has been prevalent since about 20 years ago, you get a blend of your donor and your acceptor, and very often that means that you get into at least three main phases. One that is a pure fullerene phase, one that is a pure polymer phase, and then you get a mixed polymer fullerene phase in the so-called bulk heterojunction. So in terms of the electronic processes that need to occur efficiently, you need first to have, of course, strong photon absorption. In the polymer fullerene solar cells, that absorption comes essentially from the polymer. That leads to exciton formation. At the interface between the polymer and the fullerene, you need to have efficient exciton dissociation and charge separation. Then the charges need to find efficient percolation pathways to reach the electrodes where they need to be efficiently collected. What I'm going to do this afternoon is actually emphasize that exciton dissociation process at the interface between the electron donor and the electron acceptor interfaces, those interfaces, and thus the charge, so-called charge transfer electronic states that appear at those donor-acceptor interfaces. And so that's a pretty old electronic structure diagram that we published some 8 years ago. What we are dealing with are, as not refers to the electronic ground state of the polymer. Upon photon absorption, you get to the lowest singlet excited state of the polymer. And then at the interface between the polymer and the fullerene, you get those so-called charge transfer electronic states that are key intermediate states in the charge separation. And so that CT state, those CT states can be viewed to a first approximation as having a hole remaining on the polymer and an electron that has jumped on a fullerene next to the polymer chain. And so these are still bound electron hole states. And then you need to have efficient separation with the electron moving into the bulk of the fullerene domains and the hole moving into the bulk of the polymer domains. A couple of years ago, Mike McGee and his coworkers at Stanford had published a very important paper in which they emphasized that in order to minimize the energy losses that you have because of having to go from the S1 state to a CT state and then to charge separated states, and in order to maximize the open circuit voltage, which is very often an issue with organic solar cells, what you need to have is as narrow as possible an energetic distribution of the CT states. The lower CT state energy should be also as close as possible to S1, the S1 energy. And then you need also to minimize all the non-radiative recombination pathways that would lead from the CT state back to the ground state, for instance, and which means loss of a photon. And so if I go back to my electronic state diagram, instead of that simple sketch that I had before, we need to try to design the systems, the two components and their interfaces in such a way that we minimize the width of the CT energy distribution. We need to have the lower CT state very close to the S1 state, and then we need to prevent from those CT states the non-radiative recombination pathways from singlet CT states down to the ground state and from triplet CT state down to the triplet states, for instance, of the polymer. So this is a part of the work that I will not be discussing, although we have very strong efforts in that respect. What I'm going to talk about is more how we can describe the distribution in energy of those CT states. And in that context, we have chosen to work with these polymers and the C60 Pcbm because of work that was going on at KAUST some 3 years ago, which was a collaboration among the groups of Aram Amassian, Pierre Beaujuge, and at KAUST, and Mike McGee at Stanford, but Mike leading a center funded by KAUST. Pierre Beaujuge synthesized a number of those copolymers which have along their backbone alternating electron-rich moieties, such as those benzodithiophene, and electron-poor moieties, such as those thionopyrrole diones, TPD. Now, in the jargon of organic solar cells, those electron-rich moieties are usually referred to as a donor moiety, and the electron-poor as an acceptor moiety, which is a bit confusing in the sense that that copolymer itself, in the charge separation process, the whole copolymer chain acts as an electron donor. But so in the rest of the presentation, I'd refer to the donor moiety as that benzodithiophene, the acceptor moiety as that thiophene pyrrole dione. Pierre Beaujuge synthesized with the same backbone a number of copolymers that had variations in their side chains. So either all the side chains, R1 and R2, being just straight alkyl chains, or in another instance, having normal alkyl chains on the electron donor part, the electron-rich part, and a branched acyl-exyl chain on the electron-poor part, or vice versa. And the impact is actually extremely important, because as you go from having branched side chains on the electron-rich part, which from a steric standpoint, very simply, would tell you that the fullerenes tend to go towards the electron poor part. You get really large or very significant efficiencies reaching 8%. In the other case, if you have a branch side chain on the electron poor part, pushing the fullerene towards the electron rich part, you get an efficiency that's lower than 2%. And so we wanted to understand what was going on there, what could be the reason for those differences. But as we started to do that, we realized, and that's a couple of years ago, that actually there had been very little that had been done in terms of characterizing the binding of a fullerene and the polymer chains. So we started to look at those polymer C60 interactions, and in order to go into increasing steps of complexity, we started with having no side chains on the polymer and no side chains on the fullerene. So it's just C60 with a long oligomer having no side chains. And at the level of the calculations that we used, you get fullerene polymer or oligomer binding energies on the order of 13 kilocalories per mole when the fullerene optimizes its position on top of a donor part of the oligomer. If the fullerene goes on top of the acceptor or in between the donor and the acceptor, the binding energy is basically the same. The binding energy becomes very different when the C60 comes actually on the edge of the oligomer chain, in which case you have a binding energy that's nearly half of the one you had when the fullerene sits on top of the backbone. And of course, with the fullerene sitting on top of the backbone, what you maximize is the dispersion, the induced dipole interactions among the pi electrons of the backbone and the C60. So in the absence of side chains on the backbone and on the fullerene, what we learned is that the C60 has basically similar affinities for being on top of the donor or of the acceptor parts of the polymer, which means that the side chains must play a very important role. And in the next step, what we did is to consider side chains on the C60, so turning to C60 Pcbm. And from really a very large number of calculations, we found out that when the C60, that Pcbm is on top of the chain, there are essentially three types of configurations that it wants to take on top of the chain. One in which the side chain of the C60 interacts with the pi conjugated backbone itself, one in which it is away, and one in which the side chains interacts with the side of the oligomer backbone. And then you can see pretty large differences in binding energies. In the case of that configuration, the binding energy jumps up by about 50% to reach some 20 kilocalories per mole. In the case of the second configuration, with the side chain being away, of course, that's the same thing as if there had been no side chains on the fullerene. The binding energy is the same as in the case before, 13 kilocalories per mole. So again, we see that the PCBM side chain does indeed, their orientations of those side chains with respect to the backbone do strongly impact the binding energy strength. In the case of PCBM on top of the acceptor, even in the case of that configuration, there is indeed an increase from 12 to 17 kilocalories per mole. So again, a significant increase, but not as much as when the fullerene was on top of the donor. So overall, the message is that the PCBM side chains determine where the PCBMs preferentially locate in a way that actually goes well beyond what mere steric concepts would tell you. And then we put also the side chains on the polymer. In that case, then we went to descriptions, attempts to describe the morphology at the molecular dynamics level. And we considered the 3 types of polymers that Pierre Beaujuge synthesized. And the point I would like to emphasize here is the following. In the case of the first polymer, I have only normal side chains, alkyl side chains. In the case of the second polymer, I have a branch side chain on the electron poor moiety, but that's only 1 branch side chain per polymer repeat unit. In the case of the third polymer, I put the branch side chains on the electron-rich part. I have 2 branch side chains per polymer repeat unit. So I go from 0 to 1 to 2 branch side chains per polymer repeat units. And that will be important to understand what goes on afterwards. First, we look at the polymer pure phases to see how those chains, polymer chains, can pack and the variations in packing that can be induced with the nature of the side chains. And that I don't want to go into the details here. We can discuss them afterwards if you so wish. But we looked at the radial distribution functions. That's basically taking a conjugated polymer segment on one chain and looking at where are similar segments nearby. So that gives you indeed a very good idea of how the backbones want to stack one with respect to another. And so the very sharp peak that you find in all cases, all 3 polymers at 4 angstrom tells you that you have very significant backbone packing, but that there occurs a decrease in the packing density when you have branch side chains on the donor moiety, the electron-rich moiety. Then we went to look at the polymer fullerene mixed phases. And again, did extensive molecular dynamic simulations, taking advantage of the supercomputer at KAUST. And in that case, the message from what we learned from those calculations is that there is, of course, less order in the mixed phase than what we had in the pure phase, which is what you would expect because of the mixing. But also importantly, the packing density decreases with the number of branch side chains per repeat unit, which is not surprising either. But what it tells you is that if the packing density decreases a function of those larger numbers of branch side chains, that means that it will be easier for fullerenes to come and interact with the polymer backbones. And that's actually what we see. Let me just tell you what this table is about. We are looking at the 3 different polymers. We have in the simulations box exactly the same number, total number of fullerenes, and we are looking, those capital N values refer to the number of fullerenes that come next to the donor or the acceptor, and the total fullerene numbers of fullerenes that are in interaction with the polymer chain, so the sum of the first 2 numbers. And what we get is, as the number of branch side chains on the polymer increases and the backbone packing density decreases, you get a larger number of polymer PCBM interactions. So that's, I think, pretty logical. And with respect to the power conversion efficiency that you get in the solar cell, the best correlation that you find is with the number of fullerenes actually interacting with the acceptor, the electron poor part of the polymer chains. So you get a correlation between the number of fullerenes interacting with the acceptor part and the PCE. And actually, what Frédéric Laquet and coworkers at KAUST have shown is that what happens when the fullerene gets, there is an increased number of fullerenes next to the electron acceptor part of the polymer, you get a lesser charge recombination for both geminate and non-geminate electron hole pairs. You might remember that what we were looking for was an idea of the energetic distribution of the CT states. And I've told you that we had many configurations that the PCBMs can take around the backbone of the polymer. But besides that, there is something that struck me because that's something that I should have thought about many, many, many years ago, and then never occurred to me before what we did a couple of years ago. And that's the fact that, of course, all those molecules vibrate. What I've been telling in my papers since, I'm afraid to say, the early 80s is that in those pi-conjugated systems, what makes their physics so rich is the fact that you have that strong connection between the electronic structure and the geometric structure. You change the geometric structure, you change the electronic structure to a significant level in terms of the frontier molecular orbitals. Well, those molecules vibrate. Even if you go to 0K, you get a very significant vibration. And because of those vibrations, there are some of them that couple very strongly with, for instance, in the case of PCBM, with the LUMO level. And that leads to the fact that just because of the vibrations that you cannot avoid, and actually the situation is not much worse at 300K at room temperature than it is at 0K, you get a fluctuation in the HOMO or LUMO levels that can be as large as something like a full width at half maximum of 150 millielectron volts, which is very significant in the context of what we are talking about. But then, indeed, you have also those fullerenes coming in very different configurations along the chains, and you can easily expect that if you have different configurations of the fullerenes on top of the donor or the acceptor, you'll have differences in the electronic couplings between the chain and the fullerene, and that will lead to a distribution in the energy of the CT states, the charge transfer states, that will be significant. And actually we get CT state energies that evolve between 1.2 eV and 1.8 eV, so over 0.6 eV in that case. And you can nicely fit the distribution into a Gaussian. And even if the standard deviation is pretty small, of course, the whole issue is that you have quite a lot of those states, CT states at lower energy. If the CT state is low in energy, you get a lower open circuit voltage. So the distribution of configurations and the dynamics in the system, the individual vibrations, as well as the differences in the morphologies that you can get in the polymer fullerene configurations, does indeed lead to a very substantial distribution in the energy of the charge transfer states. And the conclusion that you can make is that in order to achieve a narrow distribution that really requires to have a very limited set of preferred configurations, which is, I think, something that Barry is looking into very much. But the point is, this is maybe the reason why actually we need to switch to non-fullerene acceptors, not only because with non-fullerene acceptors you can get a much larger absorption within the acceptor component of the cell, but also because they might actually lock in much more strongly preferred configurations of the donor-acceptor complexes. And so that's the reason why I think that there is really a bright future in front of us. Of course, in the case of OPV, what you want to exploit is the fact that you could have flexible cells. And that was not because I learned last night that Jim spent quite a bit of time at Konarka, but one of the very first applications of OPV are those flexible thin films on top of bus stops in San Francisco that provide power to give light to those bus stops at night. And this is actually a picture that has been taken close to the apartment of my daughter who's here. My wife is hiding behind there. But these are, this is an application that has been already set up something like 7 years ago, I think, 6 years ago. And so they are still working. And along Gary Boulevard, for instance, you'll see many and many of those red-topped bus stops. And then there is a larger scale application that has come up of the work, the development of organic solar cells, molecular organic solar cells at Mitsubishi Chemical with 3M. And that's the development of solar cells, thin films that are put on the windows, on the facades of buildings to provide not only some power, but also some shade to the occupants of the building. The module efficiencies remain pretty low, on the order of 3 to 4%, as I understand, but things are moving up. And for instance, now in the case of non-fullerene acceptors, which brings so much more flexibility in terms of the pairs of donor and acceptor components that you can pick, there are now papers showing about 12% efficiency. At the MRS meeting a couple of weeks ago, Dr. Hao from the Chinese Academy of Sciences reported a cell certified, of course a small cell, but certified at 13%. He didn't disclose the exact composition because the paper is still under review at JAX. And I think there is a clear path to reach what was for a very long time considered to be really a major milestone, that is a 15% efficiency. So I think with indeed those non-fullerene acceptors that the next step in organic photovoltaics can be made. And with that, I'd like to thank you very much for your kind attention.
Thank you very much, Jean-Luc. We have some time for questions.
Thanks for the talk. I'm curious about the sensitivity to the polymers to heating, and whether how much, I mean, in terms of how the efficiency or the stability of the cells related to have them in full sun and they heat up to, say, 60 or 70 Celsius.
So I'm, of course, I mean, not the best person to talk about the long-time stability. Now, Carleo was my predecessor as director of the Solar Center at KAUST. He was also one of the founders of Eliatech. And what I understand from the work at Eliatech, where they use actually tandem solar cells. So they're already over 13%, but in tandem, that stability is extremely good. I mean, he's talking about hundreds of thousands of hours. Now, one of the things that's also interesting with organic solar cells is just from a general standpoint. One is the fact that actually the cells usually perform better at a higher temperature, which is the opposite of silicon. And also that they can perform pretty well at low light intensity. So you can also think about indoor applications. And then there are the other types of applications that Lynn is working on, for instance.
What are the odds of getting the efficiency up to 15, 20%?
So 15%, I think, is very achievable. I mean, I think when I see, did I hear correctly? You were saying 15, 1.5, right? Yeah. Of course, 50 would be even better, but then there are many other things that need to happen, and I guess going tandems or, but in the case of 15%, I think that what I see lately with the efforts that have started to be put into non-Fallorine acceptors, when I see the rise of the efficiencies that people are getting, I think 15% is really a reasonable thing that will be achieved. So as I said, at least at the level of research cells, but certified cells now, it's 13% for a single cell. And so yeah, I mean, I think the path is there for 15%.
Thank you. So, this is on? Okay. I was just curious. I didn't know that organic PVs operate better at higher temperature. So that was news to me. So can you explain the mechanism for that? Because I understand the mechanism of why the inorganics work less well.
No, I'm not. No, that's a good point. I have taken that more like, you know, what has been reported, for instance, by folks like Carleo, and I've not seen really a good understanding of why that's the case, but that has been repeatedly shown in the case of organic solar cells.
Because it seems I mean, it seems to go exactly, opposite to what you were showing, which is that, of course, if you have vibrations, which happen at higher temperatures, that will lead to a broadening of your energy level.
No, not really, because as I meant, well, I mean, what I failed to mention, I said, well, there is no much difference with respect to 0K and 300K. And the reason is because the modes that couple are high-frequency modes. So we are talking about CC stretching or ring breathing that are more at the order of 1,500, 1,600 wave numbers. And so it will not matter whether you're at 0, 300, or 400K in that context.
Okay, so that's a reason for it not to degrade, but still not clear why it's better.
Yeah, that I do not know. Was there anything at Konarka that?
There was speculation, but I don't think a solid proven understanding. Yeah. But very repeatedly measured, so well characterized that it improved up to 40 to 50 C.
Which is good.
Jean-Luc, so maybe this is moot because you ended the talk by saying, well, we should move away from fullerenes. But I was hoping you could talk a little bit about the design rules. So, I mean, you showed the donor and the acceptor, and the C8 on the acceptor, and the ethyl-hexyl on the donor was better. And there was this argument about solubility, if you will, on the molecular level and the interactions between the side chains. So I mean, so one can argue that if you take away the C8 or make that shorter, then there will be closer acceptor, the fullerene and acceptor contact. Has that been looked at, and is that better?
So,
or are there any design rules with respect to alkyl chain that we can learn that are more broad?
So I think what you really want to do in order to get to a short distribution of the CT states, which is what we are after, is really going into an increased order. And in a sense, that's what Barry is showing. Also, if you get to a band type, so much order that you get to a band type system, that then from that, taking that as a reference, you lose much less. But of course, so far, to get to a band type system, you're at a lower energy. So I think that the case in terms of, well, to move away from fullerenes or quite a few. I mean, there is the cost, especially if you go to C70. There is the lack of significant absorption, so everything has to be done in terms of absorption within the polymer or the small molecule donor. And then there is the added flexibility in terms of indeed finding the right combination. And that's the reason why I think that indeed there is a path to 15%, because one can find a better pair of donor acceptor that on the one hand can provide for very complementary absorption, and on the other hand could have locked configurations at the interface that could lead to a much smaller CT state energy distribution. And then the other aspect is of course understanding the best compromise between delocalization of the electronic wave functions at the interface and making sure that that delocalization doesn't lead to a lower CT energy. And so the fact that you have now two components, I mean, it makes the game more complicated, that's for sure. But to me, it's telling me that maybe there will be, you know, two families of donors and acceptors that will lead to a much better, even a much higher efficiency.
Yes.
Are there any concerns with, let's say, expensive or rare materials in either the cell or the electrodes that would be required in the organic PV?
I didn't.
Is there any concern about rare materials, non-abundant materials used in the OPV?
Well, I mean, in the OPV themselves, basically not. Of course, you might have, in terms of the catalysis of some of the synthetic steps, there might be some non-abundant elements, but in terms of the molecules themselves, no. It's one of the, that doesn't mean that some of the syntheses are not complex and costly, so that there is also that part that needs to be taken into account. But in general, no, that's not an issue with the organic solar cells. And in the case of the perovskites, that's really the inorganic part that can be the issue in terms of well, having lead and so on.
I might add that at Canarca, the biggest cost factor for production of the organic cell was the barrier layer. At the time, the best was a 3M barrier, and that was single because you needed two, one on top, one on bottom. That was the most expensive component by far of this system.
There are no other questions. I'm going to hand it over to Lynn.
Well, on behalf of the Andlinger Center, I'd like to thank Jean-Luc again for coming and thank Sigma-Aldrich for your sponsorship of this lecture. Before I let you go, we have a small token of appreciation for you coming here.
Oh.
So this is the poster that advertised your lecture, and it's signed by all the Andlinger faculty members. So thank
Very
you
nice.
again for coming.
Thank you, Lynn. Thank you. Thank you. And if Monique is worried that we have to bring that back, I'm sure
we'll
you
ship
will
it back.
ship
We'll
it.
ship it back for you.
Yeah.
And I think Jia
nice.
Choi from Sigma-Aldrich has a souvenir for you as well.
This is very nice. Very nice. Thank you, Gia. Thank you. Thank you. Thank you very much.